Okay, let's go ahead and start talking about if you can't measure it, you can't prove it. Quote here from Vince Lombardi: "The only place success comes before work is in the dictionary." So, jumping down to our learning goals, students should be able to perform mathematical operations with significant figures. So, we are going to talk about significant figures, why they are important, and then we got to do math with significant figures. Number two, we're going to convert using metric prefixes for prefixes between nano and giga without a chart. So, we need to be able to do that for the rest of the year between nano and giga. Convert between Celsius, Fahrenheit, and Kelvin. So we want to be able to convert temperatures. We've probably done this before, but we'll go it over again. Number four, we're going to memorize the 42 common elements in this course. So we're going to look at 42 elements that's really helpful for us to know. 42 elements that I expect you to know and know the place on the periodic table very well. And then number five, use atomic mass to calculate molar mass. So jumping into this, we're going to first start talking about significant figures. Significant figures indicate the degree to which you measured an object. It's telling us how accurate and precise that something is. Calculations cannot indicate greater precision than you can actually measure. So we can't say have 8 million decimal places, 1.0 0.00000 and just keep going out until infinity like what it looks like on our calculator. We can't do that. We cannot be more precise than what we can actually measure. Now, significant figs or sig figs have a real and functional purpose. When we actually use these significant figures, when NASA uses them to calculate and send things out into space, we actually need to make sure that we're paying attention to it, and especially when we're looking at subatomic particles and looking at those things, we need to make sure that we're being accurate and basically measuring to what accuracy we can. So rules for significant figures. Number 1 through 9, they're always significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, always significant no matter what. Really what comes into play that gets confusing for significant figures are rules for zeros. Placeholders, zeros are not significant. So an example of this would be 100. Those zeros are placeholders. They're not significant. The second one, zeros between other digits are significant. So an example of this would be 101. So that zero right there, since it's between that one and that one, it becomes significant. So it's a significant figure. And then lastly, zeros after a decimal place are going to be significant. Example of this, where we have 1.00, those zeros will be significant because they are after a decimal place. One more we would probably put in there, leading zeros are not significant. So if we have 0.010, these zeros are leading zeros, they're not significant, so no for those. The one after, there should be a 1 right here, the 0 after that 1, that is significant because it follows a non-zero digit in a decimal. So that's just how we count significant figures, and more on that to come. But here's the math with significant figures. So how we do math with it. With adding and subtracting, all we do is align the decimals and all the numbers, identify the most precise digit they all share, and then do the math and round the digits they all share. So an example of this would be 1.0 plus 1. We add those up. The one digit that they all share is right here. So when we add that up and get 2.0, we would just round to here. So the correct number of significant figures would just be 2. Moving on to multiplication and division, determine the number of significant figures in each, do the math, and round to the lowest number of significant figures. So if I have 2.0 times 2.00, this 2 has 2 significant figures. This 2 has 3 significant figures. So 2 times 2 is 4, but we need to make sure we have 4.0 because the answer must have the lowest number sig figs, which would be that 2. So let's jump into some examples. It says how many significant figures are in the number. So when we're looking at these, the front two, nope, they're leading zeros, they don't count. This 0 right here, we know that it's in between those guys, so that counts. So we have 1, 2, 3, 4, 5, and these would be our trailing zeros after a decimal, after a non-zero digit, so they would be significant. So we would have 1, 2, 3, 4, 5, 6, 7. 7 significant figures in that number. Moving on to the next one, a student measures the perimeter of a textbook with 4 measurements shown below. What is the perimeter of the textbook? So all we do here is we add these up. So 11.8 plus 12 plus our 8.47 plus our 8.4619. Okay, we add all these up. The one digit that they all share, going to be right here. So when we add it up and we put it in the calculator, we get a number of 40.7319. But we have to round to the ones place, which when we do that, does that 7 round that 0 up? Yes, it does. So we just get correct numbers. Significant figures would be 41. And then our last example, it says the density of a nucleus can be measured by dividing the mass by the volume. So here's our mass, all divided by our volume. So it's division. And so we want to determine the density of a hydrogen nucleus. So when we're looking at this, we look at the number of significant figures. And when we're looking at this, on the top one we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then on the bottom we have 1, 2. So when we're dividing, we use the least number of significant figures. So this would just be 2. So we would take the number in the calculator and round it to 2 sig figs, which would be 2.3 times 10 to the 17th. And the unit would be kilograms over cubic meters. Okay, when we're doing significant figures with scientific notation, the only thing that counts is what's up front. So we have 1, 2, and we divided 1, 2. That's the lowest number of sig figs, so that's what counts. Now, moving on to conversions. Why do we convert? Why is it important to convert? Measurements cannot always be done in standard units, measuring circumference and diameter. So if we would measure the circumference of this or the diameter of this, it can't always be done in standard units. Fundamental constants are often used in formulas requiring standard units. So in certain formulas, we're going to have things in liters. We're going to have things in moles. Okay, these are things we'll talk about. They have to be in those units for those equations, but we don't measure things in liters in the lab. We don't measure things in moles in the lab. Okay, normally in chemistry, we measure in milliliters. In moles, we normally measure in grams. Okay, we don't always measure in the unit that we need, so we have to be able to convert to use them in equations. Now, some very simple conversions that we should have done from the past and everything else. It's metric conversion factors. Memorizing these would be really, really important. So when we're looking at this, when we're looking here, we can look at, here's our base units. So liters, meters, grams, seconds, newtons, joules, that's what we have. When we're looking at this, those are going to be our base units. And when we look at it, a kilo is times 10 to the third greater than the base unit. So it's 1,000 times greater than the base unit. So when we say this, we say that 1,000 grams equals 1 kilogram. Okay, we could say 1,000 liters equals 1 kiloliter. When we look at mega is going to be a times 10 to the 6th greater than our base unit. So when we're looking at this, we have, if we're looking at 1 gram, so 1 million grams equals 1 megagram. Okay, that's when we're looking, it's a million times greater. So when we're looking at this, this is just how we convert to our base unit. That's what our base unit will be for one of these guys. So when we're looking at this, we can say that our micro anything, pick gram, is going to be a million times smaller than our base unit. So let's jump into some examples. It says how many milliliters are in a gallon of milk, which a milk is 3.78 liters. So we already did that conversion for us, gallon to liters. Now all we have to do is take it into milliliters. Now when we're doing this, we use a system that's called dimensional analysis to do our conversions. And all dimensional analysis is it helps us set up how we convert. So the first thing we do when we're doing dimensional analysis is we write our statement of equality. So this equals this. And in this case, we're looking at milliliters and liters. So when we're looking at this, there is 1,000 milliliters in, which equals 1 liter. Because we know that a milliliter is 1,000 times smaller than a liter. So this is our statement of equality. Our next step of what we do is we start with what we're given. We're given 3.78 liters. And when we set this up, you can kind of think of them as boxes. Now what we're looking at is we see liters here. We look at our statement of equality and we take that liter and it has to match. We put so that whatever's here must be there. Okay, and then we take one part of the conversion factor, put it on the bottom, take the other part, put it on top. And all we do is we multiply it out, 3.78 times 1,000. That's going to give us our answer, which we would get our 3,780 milliliters. Okay, that's how we convert it. Looking at our next one, a weightlifter is capable of bench pressing 250 pounds. What is the mass in standard metric units? In most units often used in chemistry. Okay, when we're looking at this, our standard metric unit, we would be looking for kilograms. In chemistry, we measure things in very small amounts, so therefore it will be in grams. So when we're looking at this, we have 250 pounds. Well, to go from pounds, first we'll go to kilograms. So we have to know how many pounds are in a kilogram to write down that statement of equality. So what we will do is we'll say that 2.2 pounds, and all I did was look this up, equals 1 kilogram. Okay, if you don't know a conversion factor, like you don't know how many pounds are in a kilogram, you can always look it up if you're at home. If it's an obscure one, you can always ask your teacher and they'll help you with it, give you that one. So 2.2 pounds equals 1 kilogram. So we start with what we have. We have 250 pounds. Set it up. Since pounds is right here, we need pounds right there. So we take that part of the statement of equality, put it on the bottom. Put the 1 kilogram on top. And then all we do is multiply it out. So 250 times 1 would be 250, all divided by 2.2 pounds. And that will give us 114 kilograms. Okay, so this is what we have in our standard metric unit. If I want to take it to our grams, well, we need another statement of equality. We know that a kilogram is 1,000 times greater than a gram, so it takes 1,000 grams to equal 1 kilogram. So we set it up. If kilograms is right here, what has to go there? Well, we have to have kilograms. So we take our 1 kilogram, put it on bottom, take the other part, put it on top. And then all we do is multiply the top, and then we divide by the bottom. So 114 times 1,000 divided by 1, that will be 114,000 grams. So the answer, two answers for this, 114 kilograms, that's how much 250 pounds is, and 250 pounds is 114,000 grams. Now, moving on to our temperature scale. There are three main temperature scales all throughout the world. The Fahrenheit is used by the United States. Everywhere else, they pretty much that have they have the Celsius temperature, a little different than what we have. But we have our Celsius, we have Fahrenheit, and we have Kelvin. Fahrenheit's used in the U.S. and a few other places, and then Celsius is used everywhere else. And then Kelvin is what's used for science. So when we're looking at temperature conversions, we always use Kelvin or Celsius depending on our circumstance in science. When we're using Kelvin, or converting from Celsius to Kelvin, this is the equation that we use. If we're converting from Fahrenheit to Celsius, this is the equation that we use. So let's jump into an example. It says convert 100 degrees Celsius and Kelvin. So it probably should say to Kelvin. So when we're looking at this, all we have to do is Kelvin equals our Celsius temperature plus 273. Okay, the way you can remember this, Kelvin is based off of a temperature scale with absolute zero. That Kelvin can never be negative. So anytime we're converting to Kelvin, we always add 273. So on this, we just add our 100 plus 273. That will give us an answer of 373 Kelvin. Jumping on down to the next one, it says the temperature in Germany is 38 degrees Celsius. How will you dress? We want to justify our answer. Okay, when we're looking at this, it's 38 degrees. So what we would do is we would use our equation that our Celsius equals our 0.556, all that times our Fahrenheit minus 32. So when we're doing this, we know our Celsius is 38 equals our 0.556. We're trying to find our Fahrenheit because we really deal with Fahrenheit here in the US. So to do this, we go ahead and divide this out. So we'll take our 38 all divided by our 0.556, and that equals our Fahrenheit minus 32. So to get Fahrenheit by itself, we'll just go 38 all over 0.556. Put that in parentheses, plus 32 equals our Fahrenheit. When we plug this into the calculator, if we do it correctly, we should get something right around 100 degrees Fahrenheit, which is extremely hot, which we would probably wear some shorts and a t-shirt. Okay, moving on down, jumping into chemical symbols and elements. There are 60 million chemical compounds that have been identified and registered. All compounds are a combination of just 114 elements. So there's not a lot of elements, but they combine to make over 60 million chemical compounds. And all elements have a name, a chemical symbol, atomic number, and atomic mass. And we can see that here. There's our atomic number, there's our symbol, and there's our atomic mass. So our periodic table today is organized by the atomic number, the number of protons, but we'll talk more on that later. And number two, it displays a great deal of information about each element. A good periodic table to use is ptable.com. Make sure you go to that, bookmark it on your computer so that you can go to it and use it when you're at home. Great periodic table is ptable.com. Jumping in, our 42 common elements in chemistry. You can go ahead and pause it right here and take a look at all of those. These are the ones that we expect you to know, expect you to be able to do. Jumping down into a developing problem, our first example, it says, using a periodic table, what is the name of the element that starts with the chemical symbol of a V? Okay, we look on the periodic table, we find V, and it stands for vanadium. So we have that one. Now, jumping into atomic mass. Atomic mass is displayed at the bottom number for each element in the periodic table. It's a unit of atomic mass. They are grams per mole. So here's our atomic mass. It's at the very bottom. So in this question, it says use your periodic table. What is the atomic number and atomic mass for iron? We should probably go back and say atomic number is right there. Atomic mass is right there. So looking at this, it says what is the atomic number and atomic mass for iron. So iron, we would look on there, iron is Fe. So when we're looking at this, that would be iron. Its atomic mass should be right around 55.845, and the atomic number would be 26. Now, jumping into molar mass. Molar mass, we call this gram formula mass. It's the amount of mass in 1 mole. Most chemical compounds are not a single element, but a combination of multiple elements, such as table salt, which is NaCl. So to find the gram formula mass, we have to add up the mass of sodium and the mass of chlorine. So sodium has a mass of right around 23, and chlorine is right around 35.5. We add those together because we have 1 sodium, 1 chlorine, and we get 58.5 grams per mole. So let's do an example. It says, what is the molar mass of KBr? So when we're looking at this, it's potassium and bromine. So we look up the mass of each. The potassium will be right around 39.1, and bromine is going to be right around 79.9. We add both of these up, and we get a molar mass right around 119 grams per mole. Next example, it says, what's the gram formula mass of iron 3 chloride? So when we're looking at this, we have 1 iron, and we have 3 chlorine. So to find this, what we would do is we have 1 iron, which is 55, right around 55.8 grams, and then we have 3, because that 3 right there tells me we have 3 chlorines, so 3 times 35.5. We add both of those guys together after we multiply 3 times that, and we get right around 162.3 grams per mole.